You might be wondering, what is a capacitor? And the concept is pretty simple. It's any two conductors separated by an insulating layer. And the two conductors are called plates regardless of the shape that they have. Now the concept is simple, but understanding what's really going on does take a little bit of finesse, I'll say. So let's take a look at an example when a capacitor is connected to an EMF. The first thing is that the EMF sets up an electric field in the circuit, causing electrons to move. And recall that the current is defined as the movement of charge. And as the electrons move, that's the flow of current in the circuit. Now, of course, the current direction assumes that we have positive charge carriers. So in this circuit as drawn, charge would flow from the positive terminal of the EMF clockwise through the circuit to the negative terminal of the EMF. By setting up this electric field in the circuit and causing current to flow, the EMF actually ends up moving electrons around, and it removes electrons from the top plate of the capacitor and then places them at the bottom plate of the capacitor. And when electrons are removed from the top plate becomes positive. And then as the electrons are placed on the bottom plate then becomes negative. And you consider this going on one electron at a time. So if we imagine that one electron is removed from the top plate, I guess first understand that an uncharged capacitor has no net charge, and there is no accumulation of charge on either plate. They both have a net charge of 0. But we're going to be talking about QT as the charge on the top plate and QB as the charge on the bottom plate. So once the electric field gets set up and electrons are moving and we have current flowing, one electron gets removed from the top plate, and when you remove an electron, because the number of protons stays constant, that means that there's a positive charge on the top plate. And that electron gets attracted to the positive terminal of the EMF, so it goes counterclockwise through the resistor to the EMF, and then the EMF actually pushes it down, and it's like a charge escalator. In this case, it's pushing the electrons down. And then the bottom wire is all at the same potential, so that extra electron ends up on the bottom plate of the capacitor. Now, really, the wires are filled with free electrons, and so there's one that gets removed from the top plate and then goes into this mass of free electrons, and there's one free electron on the other side, the bottom wire, that ends up being deposited on the bottom plate of the capacitor. In any case, the important result here is that QT is equal to negative QB. So the net charge on the top plate is always equal and opposite to the net charge on the bottom plate, and therefore the total charge on the capacitor is 0. But when we talk about the charge on a capacitor, we actually just then talk about the charge on one plate, because it's true that QT plus QB is going to be equal to 0, and talking about the net charge in terms of both plates of the capacitor doesn't really give us anything useful in terms of talking about circuits. But if we talk about just one plate at a time, then things get really interesting. And you know when a physics prof says interesting, that it's going to get tricky. And the process will continue. The EMF will continue to remove electrons from the top and deposit them at the bottom. And it will always have the same number of electrons removed from the top as deposited at the bottom. But then what happens is that charge builds up in this case on the top plate, and charge builds up on the bottom plate. And again, those charges are equal and opposite. And by convention, when we talk about the charge on a capacitor, we're really just talking about the charge on one plate. And we typically only take the positive value of that. We take the absolute value of the charge on one plate. In some rare questions, you'll actually have to consider the positive and negative separately. But most of the time when we're actually working with the circuit equations, we assume that it's just a positive charge on the capacitor. The next thing I'll do is take a look at what I get by applying the loop rule. In this case, I get that the EMF minus IR minus VC, which is the potential difference across the capacitor, is equal to 0. And so as the EMF drives current through the circuit and removes electrons from the top plate and it deposits electrons on the bottom plate, the voltage across the capacitor, VC, will increase, and it will keep increasing until the voltage across the capacitor is the same as the voltage across the EMF. And looking at the loop equation, Vc can only be equal to the EMF when IR is 0, which means that the current is 0 because the resistance would never be 0. And at this point, we would say that the capacitor is fully charged. And here, fully charged ends up being kind of a set of keywords that helps you interpret word problems so that you can know something about, say, the voltage across a capacitor if it tells you that a capacitor is fully charged at a certain time. Anyway, you'll have to practice with some problems and just understand that fully charged has a very specific meaning. Now, noticing that the current is 0 when the capacitor is fully charged gives us a general application or a general guideline that a fully charged capacitor behaves like an open switch. There's no current. We can contrast this with an uncharged capacitor, and uncharged is a keyword meaning that Q equals 0. And an uncharged capacitor has a voltage difference or a potential difference across it of 0, and only for an instant behaves like a wire. Then we get to a definition of capacitance, which is just that the capacitance of a capacitor, C, is equal to the charge on the capacitor, Q, divided by the voltage across the capacitor, which is Vc. And the units for capacitance are Farad, where 1 Farad is equal to 1 coulomb per 1 volt. And you'll often see this equation rewritten as Q is equal to C times V.